do you guys want? I assume you want me to go through the equations again. Okay. All right. So we've got. All right. Number one, work equals force times. I'm going to say distance here just because that's what it's usually referred to as. And then cosine theta. Usually that cosine theta doesn't really matter. I'm not writing very well on this. 2 kinetic energy equals 1/2 mv squared. Gravitational potential energy equals mgh. Elastic potential energy equals 1/2 k delta x squared. And since it's 1/2 k delta x squared, what do you think is going to be in relation to something else? Not quite. If you take the derivative of that, what do you get? Usually when you see a 1/2 and k delta x, you'd get the force. So it usually, just so you guys are aware of this, usually when you see the 1/2 out in front and then a term squared, that means it's the integral of something else. That'll come into play later in calculus, but usually it means, so usually if you see a 1/2 k delta x squared, that usually means you got that equation was obtained by taking the integral of something else. So if you take the derivative of that, you get back to what it originally was. It is the antiderivative as well. And power equals work over time. These all look familiar? And I'll write down number 6 is the big long one. Work plus original kinetic energy plus and just so you know, we refer to these by how they sound, so this Kio, Pego, Pexo. That'll be Kef plus PegF and PexF. And just so you guys know, a lot of times you'll see PE, like potential energy, is going to be written as U, like a capital U. I use PE because it makes a lot more sense than using U. So, alright. Alright, what amount of work can a 500 watt motor do in 5 minutes? So what is the first thing we're going to need to do since we have minutes? Let's make that seconds. 5 minutes times 60 seconds in 1 minute. 300 seconds. So that's our time. And what equation we're going to use here? I like to start you out in a nice easy one. So we got 500 watts equals work times 300 seconds. And what is the total amount work done by that motor in 5 minutes? 150,000. And that is joules. A worker pushes a box with a horizontal force of 70 newtons over a level distance of 4.0 meters. If a frictional force of 59 newtons acts on the box in the direction opposite to that of the worker, what is the net work done on the box? Alright. We don't have to use anything from last chapter. So we're going to have two different works, right? So to find the total work, it's just going to be work total. It's going to be the work done from pushing. And are we going to add or subtract the work done by friction, do you think? Subtract. Work done by friction is almost always going to be negative. Except when it's positive. That is correct, Paul. Alright. Except when he gives us a problem that we've never seen before. When you add it, why is it added? What? Why is it added? Why do you have what you have written? So the total work is equal to the work you're done by pushing it minus the work done by friction. Okay, because the friction work's wasted. Yes, friction work is against the other work. Alright, so we're going to have force times distance for both of those. So for the pushing, it's 70 newtons. And our distance is 4 meters. Minus 59 newtons. Times distance is also 4 meters. Keep making it 40. And what is the total work done in this problem? 44 joules. It's going to be a year-long thing now, I think. Here, we won't put it on the video. Equals 4.4 decajoules. This next one is the first one that's a little bit more difficult. This should say 30 degrees, not 30 box. Alright, so alright, a 44 Newton crate starting at rest slides down a rough 8.8 meter long ramp, inclined at 30 degrees to the horizontal. Force of friction between the crate and the ramp is 9 newtons. Find the velocity of the crate at the bottom of the incline. We could actually do this problem with the stuff we've learned in the past, right? Okay, but we got to figure out some things first. But we're going to do it with energy, and it'll be a lot easier, I promise. Alright, so our angle is 30 degrees, and this is 8.8 meters. What kind of energy is the box going to have to begin with? Potential. And we'd probably like to know the height, right? So let's find the height. So the height's going to equal sine 30 times 8.8. So what is the height of that ramp? 4.4 meters. Alright, any questions? How we got that? Alright, so now let's think about that big, long equation. So, is there work being done in this problem? Yes, what's doing work? Gravity, but we're going to incorporate gravity with potential energy, right? Potential energy is equal to the work done by gravity. Or potential energy lost. What other work is being done? Friction. So we're going to have, and we're going to add or subtract the work done by friction, do you think? Subtract. So we're going to say negative work done by friction. So next thing we look at is kinetic energy. Is there kinetic energy at the beginning? No. So no kinetic energy, so we don't write that. Is there gravitational potential energy at the beginning? Yes. So plus pego. Is it touching a compressed spring at the beginning? No. So we don't need that. That's for elastic potential energy. Is it moving at the end? Yes, so we do have Kef. Is it above the ground at the end? No, so we don't have PegF. Is it touching a spring at the end? No, so we don't have PexF. This is our equation. So we've got negative force times distance, that equals, plus mgh equals 1/2 mv squared. So what else do we need? We have the weight of the crate. We'd probably like to have the mass of the crate would be nice. So let's find that. So we've got Fg equals mg. So 44 equals mass times 9.8. And what do we get for the mass of the crate? 4.49? So 4.49 kilograms. Now we just substitute into this equation. So we get negative 9.0 newtons. What's the distance the force of friction goes through? 8.8 meters. And now we've got plus 4.49 kilograms times 9.8. Found our height to be 4.4 meters equals 1/2 times 0.49 times v squared. What? You only had to use one equation. You had to use lots of things to do it with our old stuff. Now, did we get 7.14? Alright. Any questions on how we got 7.14? So, this is the last one we'll do together. They will get kind of hard later on. This one's not that hard. Because you guys are fully capable of doing the hard ones on your own. Alright. No, that's the next section. Alright. So a spring with a spring constant of 2,330 newtons per meter is compressed 0.81 meter to launch a 1.6 kilogram box along level ground. How far from the spring does the box come to a stop if the coefficient of friction is 0.22?
Wait, do we have to account for friction as the spring is decompressing?
No, we're going to say we do not need to account for friction during that 0.81 meters.
Okay,
Alright, so let's go through and figure out what kinds of energies we have. So first thing, is any work being done? Yes. What's doing work? The spring, but we're going to incorporate that into the elastic potential energy of the spring. Friction. So friction, like we said, is going to be negative, so we have negative work done by friction. And then, is it moving to begin with? No. Is it above the ground to begin with? No. Is it, it is with the spring. So we got plus pexo. What about at the end? Is it moving at the end? Is it above the ground at the end? Is it touching a spring at the end? No. So it just equals 0. No, they launch it. So what's happening here? There's a spring. And then it's going this way, and then eventually it just stops because of friction. Alright, so we've got negative force times distance plus 1/2 k delta x squared equals 0. We don't have the force of friction this time. But how can we find the force of friction? Yeah, Fn mu, and it's on flat, so what's Fn going to equal? Mg. So we're going to say negative mu mg times the distance plus 1/2 k delta x squared. One thing I want to make sure you guys are careful of in this is because of, especially when you start out here, because of what you did last chapter, it's very easy to forget the distance in there and just put mu mg, because you're used to just putting mu mg for the force. Alright, spring constant is how stiff the spring is. Yeah, it's right here. Alright, so we got negative, it is not unitless, 0.22. Mass is 1.6 kilograms, 9.8, times distance, which is what we're looking for, plus 1/2 times 2,330 times 0.81 equals 0. Alright, so what is our distance it traveled before it stopped? Alright, any questions on this? 0.81 squared.